Okay, then let's try to solve this example. That example is about the combined cycle analysis. What you're going to do is that we are going to analyze the Brayton-Rankine combined cycle. Please give a pause of this video lecture and try to read this statement and think about how to tackle this problem. Okay, so let's try to calculate this Brayton-Rankine combined cycle analysis. Now there are given conditions. So topping Brayton cycle, which is the model of gas turbine, has a pressure ratio of 8, and air enters the compressor at 300 Kelvin, and the turbine inlet condition is at 1300 Kelvin. And the compressor and turbine are not ideal. So the compressor efficiency is 80% and the the turbine efficiency is 85% for the gas turbine. Then how about the bottoming cycle? The bottoming cycle is a Rankine cycle, and let's say that it's an ideal case. We have pressure difference between the low pressure and high pressure of the Rankine cycle at 5 kilopascal and 7 megapascal respectively. And now steam is heated in a heat recovery steam generator to a temperature of 500 degrees Celsius. And now the exhaust gas leaves at HRSG at 450 Kelvin. So we want to calculate the ratio of the mass flow rates of steam and the combustion gases. That is F. And also we want to calculate the thermal efficiency of the entire combined cycle. In order to calculate that, let's assume that the gas in the gas turbine is still air, and that is an ideal gas. But now we consider a variable specific heats. In fact, this example is continuation from previous example in example 29, where we already discussed only the gas turbine analysis. And all those conditions for gas turbine is exactly same as the gas turbine that we calculated in example 29. So please go back to the lecture note 29 to see how we tackled this gas turbine analysis. Okay. Also, in the same example, we also calculated the regeneration case. Now, we assume that we use the same gas turbine, but we try to combine that gas turbine with a steam power plant in the combined cycle concept, and how much can we improve the overall performance. So that is our question. Now, because we have Brayton cycle and Rankine cycle, now we could draw this test diagram where the blue curve is for Brayton cycle and green curve is for the Rankine cycle. And as you see, we start from 1 prime, the air in the gas turbine, and from 1 prime to 2 prime, we have compression process. Now that is not ideal. From 2 prime to 3 prime, then we have a heat addition process, and 3 prime to 4 prime, we have expansion, which is not ideal in the gas turbine. And now at the HRSG, we have decrease of gas temperature at 4 prime to 5 prime. On the other hand, the Rankine cycle has this loop, so the water starts from 1 to 2 in a pump, and 2 to 3 at the HRSG, and 3 to 4, that is ideal expansion of steam turbine, and 4 to 1 is the condensing process. Now, the first question is, how can you calculate this ratio? Okay. And by looking at the energy balance analysis in the previous page, we can write it as this equation. Now mg dot, that is mass flow rate of the air or gas in the gas turbine. Now when this exhaust gas changes enthalpy from 4 prime to 5 prime, and this much of heat should be transferred to water to change its energy or state from H2 to H3. So now F is defined as the amount of steam generated by the unit mass of air or gas, and which can be calculated by H4 prime minus H5 prime and H3 minus H2. Okay. So now this H4 prime and H5 prime can be found from the air table. So please study and practice more on to get those values by using the table of the ideal gas, air in the case, from the table at the back of your textbook, and that is quite important for now. And also H3 and H2 can be found from the water table. Obviously, in order to get this H3 value, and H3 value is already can be easily found from the given condition at 3. But in order to calculate H2, we have to go through the pump analysis. And we already learned how to do it. So I'm not going to repeat this here again. Okay, so that is, and if you calculate it, then the answer of F is 0.131. Okay, so what it means is that if you make 1 kilogram of air, we have 0.13 kilogram per second of steam. Okay. Now, how can you calculate the thermal efficiency? So thermal efficiency, again, is defined as net work divided by Q in. So we have to calculate the net work and Q in. So Q in can be calculated by H3 prime minus H2 prime from the given index. And that is per kilojoule per kilogram of gas. Okay. So now, again, we can find out these two values from the air table. And about net work, we can use the net work for gas turbine and plus F times net work for steam turbine. And that is also in the unit of kilojoule per kilogram gas. Okay. Now net work of the gas turbine is H3 prime minus H4 prime and minus now compressor work H2 prime minus H1 prime. Okay. So in order to calculate these turbine work and compressor work, we have to go through the turbine efficiency and compressor efficiency. Basically, there's repeating ourselves, in terms of what we learned in before. So again, please review the previous lecture notes to learn about how to calculate these turbine work and compressor work for the gas turbine analysis. And if you do it, then it gives us 210.4 kilojoule per kilogram gas. Okay. And if we calculate the steam case, that is H3 minus H4 minus pump work. Okay. And also we can calculate the pump work, we can calculate the steam turbine work. So from this calculation, now we have 174, and this unit is not kilojoule per kilogram gas, but is kilojoule per kilogram steam. So that is why we need to multiply F to change this unit to kilogram per kilogram gas. Okay. So if we just calculate, we already calculate 210 the net work from the gas turbine and net work from the steam turbine. So we can calculate the thermal efficiency, which gives us 48.7%. So now let's go up to compare 3 different cases. So in the example 29, we calculate the same gas turbine to calculate its net work and the efficiency. And we also calculated the regeneration gas turbine by assuming that if we have regeneration on the same gas turbine, then how much work and efficiency would be improved. And as I hope that you remember that by having a regeneration, net work does not get any benefit. so still the net work should be the same, but efficiency should go up. Okay, so now if you look at this table, we have increase of the efficiency from 27.4% to 35.6%. Then what if we use the same gas turbine and combine with the steam power plant that is given as in this example? So then the net work also can increase drastically from 210.4 kilojoule per kilogram gas to 384.8 kilojoule per kilogram gas. So that is a huge jump. Not only we can increase the net work, but also we can increase the efficiency, okay, because we can use the energy of the exhaust gas to generate the steam, and its efficiency increases from 27.4% of single gas turbine power generation to 48.7% in the combined cycle. That is even much higher than when you use a regeneration. So that is the whole benefit of using the combined cycle. We not only can get the more power, the efficiency is also a lot better, compared to the single unit gas power plant or single unit steam power plant. Okay, so that is a great benefit of a combined cycle.
Today we learned about how we can expand a simple Rankine cycle to much bigger and much more complicated system to get more benefit in terms of power generation and even cogeneration. Okay, so our conclusion is that yes, a simple Rankine cycle can be expanded with multi-stage turbines and feed water heaters for large-scale power generation. Also, the Rankine cycle can be combined with a gas turbine or other gas power cycles to make a combined cycle, or we also can make a cogeneration facility to get both power and heat that we need in terms of society. So today's lecture is the last lecture about the gas power cycle. There are many other topics that we have to cover in terms of the feeder water heater analysis or multi-stage reheating analysis, but I decided to not cover that much about those topics because of the time limit. The next lecture, we are going to move our topic to the refrigeration and heat pump. And that will be our last topic of our thermodynamics course. Thank you so much for your time and attention, and I hope that you have learned a great deal of the gas power cycle based on the Rankine cycle analysis. Have a wonderful day, and thank you. Bye-bye.